Okay, we're going to talk about rotational kinetic energy. Always remember, so this is very convenient. We have a point mass today. This is the last day. We can just work on a point. We're constrained to move in a circle. Okay, so we go along with a velocity v that's perpendicular to our radius. We can do theta if we have if we have a change in theta over time, because we're calculus students, that's omega. If we accelerate along this circle, we call that alpha. Okay, but that's just, remember, to get this radians, these whirling, whirling things, what did we do? We took the circumference of the circle and used that as a basic unit. What did we do to our circumference? We just divided by the radius. So if we want it back, if we want to switch back to linear motion along the circle, we just multiply back by radius. This W weird omega thing, it's a lowercase omega. That's V. I could just get my linear speed back. And sure enough, radians per second. If I take radians, if I take the alpha, the angular acceleration, and multiply by radius, that's the tangential, we'll call it. That's the acceleration along the circle. Okay, so it's ridiculously complicated, thank goodness. Even for College Board, it's too complicated to have a circle where we change the radius throughout the motion. We're not doing any elliptical motion. We're not doing any weird curvy squiggles. Okay, if we happen to change radius, we'll actually use energy to treat it. Like if we have a satellite that's in elliptical orbit, we're changing gravitational and kinetic energy, but energy is conserved, so we'll just use energy and not even worry about rate of change of stuff in time. So we can get exactly back to our tangent acceleration, tangent velocity. That's usually not noted. Fantastic. So, okay. Remember how kinetic energy, which College Board just calls capital K, it's 1/2 mv squared. And so it's going to actually matter. Remember, we did a dot product when we did force dot displacement was work and energy. Kinetic energy actually has a dot product with itself, but the vector has to be parallel to itself. Duh. So the cosine's always 1. So be careful with that. We don't really worry about it, but it is in there. And let's just convert that. So we just use the magnitude of that velocity. And I'm being extra careful because now we have radial velocity and it's not the same. And we could have like a total 2D velocity. That's weird. And it's not the same. This is velocity just along the circle itself. Well, let's change it over. 1/2 m. What replaces v if I'm in rotational coordinates again? W times r, right? I can change back and forth. So I have w times r squared instead of v. Oh. And for the point mass m, then your rotational kinetic energy is 1/2 times, I'll write it suspiciously, mr squared times w squared, or 1/2 I w squared. Oh, look. Okay. Rotational kinetic energy is regular kinetic energy. Using these rotational quantities, including moment of inertia, rotational inertia, is just a convenient way to write the energy or the things that it has just because it's spinning. After Thanksgiving, we'll take a step up in complication. We'll have things rolling, like rolling down a ramp, rolling through a loop. If you're rolling, then you're translating sideways and spinning at the same time. And yeah, let's not think about that till we've had 5 days off and too much turkey. Okay, but just remember, so you'll have physicists like to break things into components like x and y. Okay. K, linear, was the old one. So we'll take your linear kinetic energy would be 1/2 of the total mass with no r squareds times the velocity of the center of mass. And if I just sit there and spin and rotate, the center of mass actually isn't moving. In fact, it rotates around the center of mass. If I have some object, we're not discussing yet what is constraining this point mass to move in a circle. We just assume that it is. I can get out the toy with the string and whatever. But just keep in mind these are separate things. If you need the rotational kinetic energy, what's really fabulous is that this I is different. So we just did mr squared, which is a point. And if you have some extended object, all you have to do is, through the magic of calculus, break it up into a bunch of little point masses, like atoms are in real life. And you have to use calculus to add up, integrate, sum up all the points for all over. You might think, oh wait, that's really easy, right? Actually, no, because every little piece of mass will have its own radius from the center. So you actually have to do a really clever integral where you're accounting for how the radius changes as you move from the axis out to the edge of the object. Okay, and that's my challenge tomorrow, is to make that look as simple as possible. But for today, so that you can have like 35 minutes to try your problems. Come on, technology. If you don't have point masses, and I mentioned yesterday, college board is usually this generous. Page 510 in your textbook has all the rotational inertias for a bunch of different objects already worked out. Instead of mr squared, this is actually 1 times mr squared, and we're just too lazy to write the 1. It's 1 for a point. And it's 1 for a hoop, because all the mass is distributed right at the radius. But for a solid disk, it's actually 1/2. Did we do that in first year physics? And for a sphere, it's 2/5. So it's just some fraction times the total mass times the radius of the object squared. And we'll start tackling tomorrow. It's a journey. We'll just start tackling it tomorrow, what that is. And there's actually only one result. This is really like chapter 10, part 1. There's only one result you really need to know so far, and that's the parallel axis theorem. So at this point, you should stop and try problems up to 65. At 65, you actually need the parallel axis theorem, I think. So if you're already finished everything up to 65, you try and look at the book's explanation of it. Mine's coming tomorrow, and so you'll at least be ready. Any questions up to this point? Okay. You let me know. If we're going really fast, I can check some of your answers. Oop.